At its heart, chemistry is really all about change. It's about substances turning into other substances. But here's the thing, not all change happens at the same speed. Some things happen in the blink of an eye, while others, they can take a lifetime. So what's the difference between a flash and a fade?
I mean, just think about it for a second. An explosion? That's a chemical reaction that's over and done with in a fraction of a second. But what about the iron on a car slowly rusting away? That's a chemical reaction too, but it can take decades to play out. It's the same fundamental process, but the speeds are just worlds apart. What's the deal here?
Okay, but here's where it gets really weird. Science, specifically thermodynamics, tells us that a diamond is actually unstable. Yep, given enough time, it's supposed to transform into plain old graphite, the stuff in your pencil. So why do we say a diamond is forever? This little puzzle right here, it gets to the absolute heart of what we're talking about today. So the science that untangles all of this, from explosions to rust to why your diamond isn't turning into a pencil, is called chemical kinetics. It's the part of chemistry that doesn't just ask if a reaction will happen, but more importantly, how fast it's going to happen. So what does that really mean? Well, kinetics is laser-focused on three main things: a reaction's speed or its rate, all the different factors that can control that speed, like temperature, and finally, the step-by-step molecular journey it takes to get from start to finish. It's the science of how and how fast. All right, so if we're going to study chemical speed, we've got to have a way to measure it, right? How do we actually put a number on it? It's actually a lot like measuring the speed of a car. A car's speed is just the change in distance over a certain amount of time. For a chemical reaction, the rate is the change in the amount of something, we call it concentration, over a period of time. The basic idea is exactly the same. So one of the most straightforward ways to do this is just to watch the starting materials, what we call the reactants. We can start with a certain amount, and as the reaction gets going, that amount gets used up. By timing how quickly that concentration drops, we can calculate the reaction's speed. Simple as that. And sticking with that car trip analogy, there are actually two ways we can talk about speed. There's the average rate, which is kind of like your average speed over a whole 5-hour road trip. But then there's the instantaneous rate. That's the speed on your speedometer at this exact moment. Both of them are super useful for getting the full picture of a reaction's journey. Okay, so we know how to measure the speed, that's the what, but we still don't have the why. Why is an explosion so fast while rust is so slow? To get that answer, we need to zoom in, way in, to the molecular level and talk about something called collision theory. And the core idea here is actually pretty simple. For two molecules to react with each other, they first have to physically run into each other. Makes sense, right? No collision, no reaction. But, and this is the absolute key, the vast majority of those collisions do absolutely nothing. They're duds. Only a tiny fraction of them are actually effective and lead to a real chemical change. So for a collision to actually work, it's got to check three boxes. First, like we said, the molecules have to physically collide. That's a given. Second, they have to smash into each other with enough energy. And third, they have to hit each other in just the right way, with the proper orientation. It's kind of like a secret handshake at the molecular level. Let's dig into that second requirement, energy. It's got a special name, activation energy. The best way to think about it is like a giant energy hill that the molecules have to get over. If they collide but don't have enough energy to make it over that hill, they just bounce off each other, totally unchanged. The reaction just fails. And this energy hill is exactly why not every collision works out. See, at any given temperature, molecules have a whole range of energies. Most of them are just kind of average. It's only the small fraction of super high energy molecules, the ones way out on the tail end of this curve, that have enough oomph to clear the activation energy barrier. They're the only ones with the ticket to get over that hill. And that brings us to the final rule of the game, orientation. Even if two molecules collide with a ton of energy, way more than enough, if they hit each other in the wrong alignment, the right atoms won't be next to each other to form new bonds. It's exactly like trying to put a key in a lock upside down. It doesn't matter how hard you push. It's just not going to work, unless it's oriented perfectly. So now that we know the rules, collision, energy, orientation, we can start to think like chemists. How do we rig the game in our favor? How can we actually control the rate of a reaction? The logic here is pretty straightforward, right? If we can somehow make more of those effective collisions happen, we can speed things up. We can do this by cranking up the temperature or adding more stuff, but one of the coolest, most elegant ways to do it is by using something called a catalyst. So what does a catalyst actually do? It's pretty genius, really. The original reaction has that really high energy hill to climb. A catalyst doesn't push the molecules harder. Instead, it creates a whole new path. It's like a secret tunnel or a shortcut that has a much, much lower hill. It completely changes the journey. And the result? By lowering that energy barrier, a huge new group of molecules suddenly has enough juice to make the leap. This dramatically increases the number of effective collisions, and the reaction speeds up like crazy, sometimes by millions of times. And the best part? The catalyst itself isn't used up in the process. It's just there, ready to help the next molecule along. And this brings us full circle, right back to our diamond problem. It really highlights the two essential sides of any chemical story. You've got thermodynamics, which asks the big question, will this reaction even happen? And then you've got kinetics, which asks the practical question, okay, but how fast will it happen? So here's the punchline. Yes, thermodynamics is totally right. A diamond does want to become graphite, but the activation energy for that to happen, that energy hill it needs to climb, is absolutely colossal. So the rate is just, well, it's so mind-bogglingly slow that it would literally take longer than the age of the universe for you to notice any change. In other words, a diamond is forever purely because of kinetics. So there you have it, the secret rules that control the speed of everything, from an explosion to a diamond. It really makes you think, doesn't it? If you had the power to control the kinetics of any reaction in your own life, maybe slowing down food from spoiling or speeding up a cleaning product, what would you choose to change?